This video is about an introduction to and addition of polynomials. So polynomials are a broad topic and there's a lot to do with them, but this is, again, just the introduction to them. We're going to begin with some essential definitions. First, we'll say this: a term is a product of constants and or variables. Keyword there is product. Product means multiplication. And so let's note, terms are separated by addition and subtraction. So if a term is defined as a product of constants, then addition and subtraction would not fit within the term. Rather, those operations of plus or minus separate or distinguish different terms. Secondly, let's note that the sign in front of a term goes with it. So when you see a term, which is a bundle or product of constants or variables, then in front of that term you could see a minus sign if it's negative, or maybe a plus sign if it's positive and it's connected with other terms, or maybe no sign, which would mean it's positive if it's just out in front or on its own. Those are some important notes to understand terms. Secondly, let's say this: a single term in which all variables have a whole number, powers, or exponents is called a monomial. So polynomial, as defined above, can be broken up into monomials, which would be like single terms within a polynomial. So examples of monomials, mono meaning one, would be something like 2x, or negative 5x cubed y squared, or just a number like 7. Those fit the definition of a single term and a polynomial, so they are called monomials. Let's add another definition, which is this: the degree of a term is the sum of its variables' exponents. So let's take a look at some examples of how this definition might work. Let's consider the following terms. If I had just a term which is just a number like 3, it has no variables with it, and so therefore the sum of the variables' exponents would be 0. So a constant term has degree 0. Another example would be, what if we had 2x cubed as our term, a monomial it would be. Then notice it has a variable x whose power or exponent is 3, which means the degree of this term would be 3. Or thirdly, if I had negative 5x squared y to the 4th, then this has two variable factors in it. It's a single term because none of them are separated by addition or subtraction. Then we would call those variables' exponents, when added up, the degree of this term. So we would add up the 2 and the 4 to get a total of 6. We would call that the degree of that term. Let's go back. I forgot to mention, there's another, I guess, vocabulary word we should add in here, which is, if you go back to the examples of monomials we had previously here, the 2x, negative 5x cubed y squared, and 7, the numeric parts in front of these, so the 2 in front of the x, the negative 5, and then even the 7, those numeric factors that are usually written in front on the left side of a term, those are called coefficients. They're the numerical factors within the term. So we'll kind of refer to that word as needed, but so far we're seeing that show up in our terms as we see them in our examples. Now let's go ahead and add another definition or two to our list here in this topic. If we say this: the combination, which would be adding or subtracting, of one or more monomials is a polynomial. Okay, so finally we're seeing the more formal definition of polynomial than we've discussed so far here in this topic, and that is, if you put together monomials by adding or subtracting, you get a polynomial. So poly as a prefix means many, mono means one, so polynomial could mean many terms. Of course, a polynomial is just a general description. It actually could reference even a monomial, even though that's only one term, and poly means many. But polynomial could mean any number of terms. Now we have some special names for certain designations here. If you have one term, it's called a monomial, as we've already discussed. If you have two terms in a polynomial, it's called a binomial, bi meaning two. And if you have three terms, it's called a trinomial, tri meaning three. So these are just typical words used to describe these basic cases. Anything beyond this number of terms, we don't have a special name for. Like we don't call a four-term polynomial a quadrinomial, though you may have guessed that. We just call it maybe a four-term polynomial or a 25-term polynomial. But these three names are just the special reserved words for these types. Now let's also add the following. The degree of a polynomial is the highest degree of any of its terms. So notice we've already discussed the degree of a term. That's what we said previously. But now we're talking about the degree of an entire polynomial, which is a collection of terms. It's simply the highest of any of the degrees of any of its terms. So let's consider some examples. What if we had negative 3x squared y plus 1? That would be a two-term polynomial, also known as a binomial. And you can tell by counting the items separated by addition or subtraction. Remember, those separate terms. And so we would simply look at the degree of each of those terms and pick the highest one to represent the degree of the entire polynomial. Well, if the degree of the first term, remember we get the degree of a term by adding the powers of the variables, that would be a 2 plus a 1. There's a hidden 1 for the y power. 2 plus 1 would be a degree 3. So that's the degree of that entire term. The degree of the second term would be 0 because it's just a constant, the 1. So the higher one of those two options would be 3, which would represent the degree of that entire polynomial. Our next example is listed as x squared plus 3x minus 2. That's a three-term polynomial. Of course, the degrees of those terms in order would be 2, 1, and 0, the highest of which is 2, so that would be the degree of the whole polynomial. And lastly, our example is 7 plus 3x cubed minus 4x. And in like fashion, we just compare the degrees of each of those terms. The highest would be 3 in the middle term. Now, once you understand terms and polynomials and degrees, we can do lots of things with them, lots of algebra with them. So let's start with an example where we want to combine like terms. Now recall, like terms have the same powers of the same variables. So we're going to use that known definition of like terms and combine them by adding or subtracting the terms given. Our first example has a collection of some terms. The first set of two terms is kind of bundled in parentheses, and in those parentheses we see a negative 3x squared plus x. Then we see a plus sign after closing those parentheses, and then another bundle in parentheses of terms, those being a 4x squared plus 8x. If we want to combine like terms, we simply want to add them together or subtract. And notice that the parentheses in this problem aren't really doing anything for us. Like there are no exponents being held outside those parentheses, which would matter if there were. There are no negative signs out in front of the parentheses. Only a nothing, which would be a positive invisibly, and then a positive between these parentheses. So the positive signs don't affect the signs of terms. If there were negative signs, we'd have to distribute those first, but there aren't. So in fact, the parentheses in this problem don't do anything for us. We can rewrite everything without them. We'll just copy it down as negative 3x squared plus x, and then just string it all along, plus 4x squared plus 8x. So notice now all the terms are free to be combined without any parentheses. We have four terms here, two pairs of like terms. So we have the x squareds. Those have the same power of the same variable, namely an x squared. And we also have the single x's, the plus x and plus 8x, which we can combine. So combining the x squared terms, we'll get just a single x squared. Negative 3x squared plus 4x squared is 1x squared. You don't have to write the 1 in front of it. And then the x terms would be a plus x and a plus 8x would be total plus 9x. So x squared plus 9x would be the combined like terms form of that original polynomial. Let's try another example. This one begins with a set of parentheses containing 5y cubed plus y squared minus 3y, minus 8. Let me say that again. 5y cubed plus y squared minus 3y minus 8. Then we close the parentheses, and then we have a minus sign. Then another set of parentheses containing y squared minus 8y plus 11. You'll notice this time we have a negative sign in front of our second set of parentheses, separating these. So that negative needs to be distributed to all the terms in that second set before we do any combining. The first set of parentheses isn't useful because it's not holding an exponent nor a negative sign in front. So we'll copy down those terms just as they are. So 5y cubed plus y squared minus 3y minus 8. But now after distributing the negative sign for the second set of parentheses, we'll have a negative y squared and then a plus 8y and then a minus 11. So once we've dealt with the parentheses, all terms are now free to be combined. We'll look for like terms. We have a cubed term up front, but no other cubes, so we'll just copy that down as 5y cubed. Notice we have a couple y squareds. We have a positive y squared and a minus y squared. Well, those are like, and they would combine, but notice they're opposites. A plus 1 and a minus 1 would just cancel out, so we can ignore those. We also have some single y terms, a minus 3y and a plus 8y. Together that would be a positive 5y. And then we have a minus 8 and a minus 11. Together that would be a minus 19. So altogether, our combined like terms form would be this 5y cubed plus 5y minus 19. Let's go on to another example, one more. This one begins with, again, some bundles in parentheses here. Our first set of parentheses contains 3/8 x squared minus 1/3 x minus 1/4, close parentheses. Then we have minus, and then another set of parentheses containing negative 1/8 x squared plus 1/2 x minus 1/4. Now, like we've done, we should distribute the negative sign that separates these two parentheses into the second set, which means the first set isn't necessary, so we'll just rewrite by copying those terms as they are. 3/8 x squared minus 1/3 x minus 1/4. Then continuing on, we'll have plus 1/8 x squared minus 1/2 x and then plus 1/4 after distributing everything there. Now we'll look for like terms. Now notice we have some fractional terms going on in this example. Just be mindful and careful with this. You have to be able to add fractions using common denominators or subtract them, right? So we have some x squared terms. Those would be like. And notice they already have a common denominator. That would be the 3/8 and the 1/8. If we add those up, we'll simply get 4/8, which we can reduce in a second. Moving on to the x terms, we have a minus 1/3 x and a minus 1/2 x, but those need a common denominator. So we'll pick an LCD for 3 and 2, that would be 6, which means we're going to put our single x term over 6, and then we'll just translate these. In fact, what we should probably do, instead of just trying to jump right to it, is rewrite them both first. Let's do that. So we have minus something over 6x, which would actually be 2/6 if we use this first 1/3, but now with a common denominator. And then we'll say minus something over 6x, but this would be 3/6 instead of the 1/2. Again, just using the common denominator there. And then notice, looking ahead here a moment, we have a minus 1/4 and a plus 1/4. Those are like, and they just cancel out. So we can go ahead and continue by finishing this problem in reducing and combining the fractions. So we have 4/8, that's really 1/2. So we have 1/2 x squared, also known as x squared over 2, same thing. And then we have minus 2/6 minus 3/6. Altogether that's minus 5/6 x, and that's where we can stop as combined terms. And I'll also note that you're seeing me write these answers in what's called descending order of degree. So the highest power goes first, and then we kind of descend our way down from there. And that's kind of just been the rule. That's a standard practice in writing out polynomials, and we'll continue to see that going.